Good afternoon, all of you. In today's lecture, we will see some iterative methods for solving linear systems. So, as we have discussed before, there are methods which help us to recover the solution of a linear system. Just a minute, let me check if someone is wanting to join. No? Okay. Yeah. So, here we start with an invertible matrix A, which is a square matrix over the real number, and we start with a vector b in Rn. What we want to do is that we want to solve the system Ax equal to b. Now, as you know, Ax equal to b will always have a solution because A is an invertible matrix. So one such solution will be x equal to A inverse b. So if Ax equal to b, if I start with this given equation, we have discussed it many times that it will have a unique solution if and only if A turns out to be an invertible matrix. So let A be of the form this square matrix whose entries are of the form Aij's. That is, the first row will be A11, A12, ANN. Then the second row will be of this form. So if this is our matrix capital A and the vector x is of the form x1, x2 up to xn, and your vector b is of the form b1, b2, bn, then solving this system Ax equal to b is it amounts to solving n linear equations in n variable, and these linear equation we obtain by multiplying Ax as per the matrix multiplication rule, and you will have a matrix, you will have a column vector with n rows. So you equate each row with b. So first row of x should be equal to b1, first row of second row of x should be equal to b2, so on and so forth. And in this way you will obtain n linear equation in n variable. As I mentioned, since A is an invertible matrix, so the system x equal to b has a unique solution which is given by x equal to A inverse b. Now we will discuss two iterative method. One is the Jacobi method and one is the Gauss-Seidel method. As far as we saw was the Gauss elimination method, which was not an iterative method. See, when we say iterative method, it means that we will develop an algorithm in which the next step will depend on the previous step. For example, if I talk of iteration, what does it mean? You'll have your first step, then you will move to the second step, and second step will involve some previous computations that we did in the first step. So this way we provide iterative methods. So the two highly popular and fundamental iterative methods are the following: one is Jacobi method and the second is the Gauss-Seidel method. So the Jacobi method is given here. So this method, known as Jacobi method, it makes two assumptions. So remember that every method will be based on some hypothesis. Okay. So Jacobi method is no different. So the system Ax equal to b, it has a unique solution. This is the first hypothesis. So it means we can always start with an invertible matrix because in that case it will always have a unique solution. And second, the coefficient matrix has no zeros on the main diagonal. That is, a11, a22, ann cannot be zero. You see here in the matrix form of capital A, we just saw that a11, a12, these were the forms. So what I'm saying, everything on the diagonal cannot, each entry on the diagonal should be non-zero. Okay. So let us stay focused on the uh, hypothesis for a while, then we'll move forward. So these are the two assumptions, that ax equal to b will have a unique solution, and the second assumption is that the diagonal entries, they should be non-zero. Now keeping these things in mind, we proceed with the Jacobi method. Why? So if any of the diagonal entries are zero, because the second assumption is the diagonal entries all should be non-zero. If any of them are zero, then rows and columns must be interchanged to obtain a coefficient matrix capital A that has non-zero entries on the main diagonal. And this we can always do, because interchanging the row does not change the given solution. This we have already discussed many times in the past lectures. So one example is given in one. You please have a look. So the example here given is 0 1 1 2. Now you can see the A11 entry is A11 entry is 0, whereas the A22 entry is 2. So here we really cannot apply the assumption of Jacobi method, which we shall see fails. But first assumption that A is invertible is true, because its determinant is -1, which is non-zero. So the first condition of Jacobi method is satisfied. However, in this case, A11 is 0 and A22 is 2. So what we can do, we should interchange the rows of A. When we are doing the interchange of rows of A, we have to interchange the rows of B, the right hand side vector also, to preserve the system. So the new system is given into equation number 2, and it is as this: 1 2 0 1 y1 0 1 y2, then b2 b1. Just a minute. Yeah. So I request you to have a good look at this example, because we will be using this example later in our study of the method known as the Jacobi method. So once we are done with the example, then we will move forward. But note that, take a pause and please note that for system 2, the conditions of Jacobi methods are satisfied. So as you can see, for system 2 both the conditions of Jacobi method are satisfied. So system 1 and system 2, they both represent the same set of equations, but the only difference is that one system, that is the first system, do not satisfy the hypothesis of the Jacobi method, whereas the system 2, it does satisfy the hypothesis of the Jacobi method. Now let us move forward and finally see the algorithm. So given a system which is converted into n linear equations, a11 x1 plus a12 x2 up to, you will have n linear equations in n variable. So step 1 is, see, this is where you will see why we are assuming that the diagonal entries of diagonal entries of your matrix, coefficient matrix capital A, should be non-zero. So you, what do, you separate out x1 from the first equation, and of course it will involve x2 x3 xn. You remember that aij's and bi's, they are known to us. Just a minute. Hello, am I audible? Am I audible? Am I audible? Okay, Biswajyoti, you please join in time. Okay. So it's 3:16, correct? Even if I give you that 5 6 minutes, it will be 3:10. See, it becomes difficult for me to again go back and forth to see who has joined or who has not. And I have already started with the lecture. Yeah. So do you have any doubt? Okay. So today what we are doing, do you know Jacobi method? Okay. So you know the algorithm for Jacobi method? Okay, then it is good. Let us revise and then we will solve some questions. Okay? So you know, like given an n linear equation system, what you do in the step. So what are the hypotheses of Jacobi method? Can you tell? Is the screen visible? First of all, is the screen visible to you? Okay. Then can you tell me the hypothesis of Jacobi method? Very good. Solution exists. Yes. Very good. And what about the second one? That the diagonal entries should be. Mm, in that sense, it will work, but the more accurate assumption is that all the diagonal entries are non-zero, which means A11, A22, A33, ANN. They all will be non-zero. And why do we do that? We assume that because of the step 1. So what is the first step in exploring the Jacobi method is the following. You consider the first equation and you take x1 out, and you will get a 1 upon a11 and blah blah blah. Am I correct? This equation is correct, right? Similarly, you do it for the others. From second equation, you extract x2. From third equation, you extract x3. From fourth equation, you extract x4, and you keep on doing this. Okay. Now you can see, because we are taking 1 upon a11, 1 upon a22, 1 upon a and n, that is why we need to have these diagonal entries to be non-zero. Am I correct? Now what we do, we in the step 2 we make an initial approximation of the first solution. So let us start with an initial approximation which we are denoting by x naught. Okay, so this will be of the form x1 naught, x2 naught, xn naught. This is our initial approximation, and we substitute these values of xi into the right hand side of the rewritten equations. So this x1 naught, x2 naught, you keep, you put there, you put in the step 1. Okay, you put everywhere these values in the right hand side, and what you will get is the first approximation, which is x11, x21, xn1. Is this step clear? Okay, now you keep on doing this. So after this procedure has been completed, one iteration has been performed. Now in the same way, the second approximation you can form by substituting the first approximation's value into the right hand side of rewritten equation, and by repeated applications you will get a sequence x0, x1, x2, so on and so forth. And we, what we should hope, that they should converge to the original solution. Am I correct? Okay, you do one favor, you take this example one. Okay, you apply Jacobi method to this example with your initial approximation as 0, 0, 0. Okay, and you give me at least 3 iterative steps. Take your time. Okay, is that fine? And if at any stage you are stuck, please tell me. Okay, hello. Okay, so please apply Jacobi method on this, and if you are stuck, then please tell me. When you are done, please tell me. Okay, at least when you're done with the first iteration, you tell me the answer. Okay, So you're done. Hello. So you're done. So what is the so did you verify the hypothesis of the Jacobi method? Yes. So is it? See, this is the problem, huh? Like when you are asked to perform a method, you first check the hypothesis. Am I correct? Yeah. So please do that, and then go for the third iteration also, and tell me the limit. Okay. So first question is check the hypothesis. Second is go to the third iteration, and third question is can you see the limit of those approximations? Okay. Yeah. Are, are you done? Okay, okay. Take your time. Take your time. Okay, okay. Sorry, sir. Yes. Yes. So are you done? So can you verify up until third iteration I have written down the values? Is does this match yours? Okay. Now my question to you is, like when you are taking n 0, 1, 2, 3, it gives you a sequence, right? Sequence of approximations. So what, but like we, because we're starting with an approximate solution, but this system originally has one solution. Am I correct? Because A is an invertible matrix, so it should have a unique solution. Can you find that unique solution? We have already done so many methods up until now. At least two of them we have done. So can you find quickly what are the solutions? What is the unique solution to this system using the row operation? Because I want you to realize that the sequence of approximations that we are obtaining via the Jacobi method, this sequence will converge actually or will not. It is still a question to you that what about the convergence of this sequence to the original solution? Ideally what we should expect, okay, we have a sequence of approximations, so we might expect it to converge to the original solution. Am I correct? So please find out the original solution using either of uh, Gauss elimination method or modified Gauss elimination method. Okay. So please find out the solution and tell me. Okay. So if I give you this table, can you see that like this solution converges, this approximations converge to the original solution? See this x1 n, x1 power n, x2 bracket n, x3 bracket n. This is one vector in R3. Am I correct? and after 6 and 7 you see the first is 0.186, so it is kind of uniform. And what you are saying, this is the precise solution, right? So up to I can say up to 3 significant digit I am getting the solutions. Okay. So this happens with the Gauss Jacobi method, okay, or the Jacobi method. Now there, so another method in this sequence is the Gauss Seidel method. So Gauss Seidel method can be thought of as an evolved form of Jacobi method. So what it does, okay, let us start again with the Jacobi method. The values of xi obtained in, so like, do you know this Gauss Seidel method? So what is the difference between Gauss Seidel and Jacobi method? In the next, yes. If for example, if you are evaluating the first approximation, so then x11 will be the first element, then in x21 you will use the value of x11, am I correct? So this is the major difference between the Gauss Seidel and Jacobi method, and the rest of the thing is same. So what do you think, which one is better, Jacobi method or Gauss Seidel method? Yes, the convergence is faster. Yes. So these are, so okay, is this the same question? Let me just check. Yeah, now you, what you have done, you please apply Gauss Seidel method in this example and at least draw four approximations. Okay, but then we have a lot of time. Yeah. See, never be see, when you want to learn analysis, one thing I would like you to know, that do not be afraid of computations. See, when I was preparing this note, for example, I also did all these computations. They are right in front of you. Am I correct? It's not like I skipped any part. I sat down and I spent much time computing this approximation. So why are you afraid? Yeah, or at least give me three. Okay, if four is more, then give me three. Because see, again we will compare the Gauss Seidel and the Jacobi method and the Seidel method. Okay, so please. So how many iterations you have computed, Biswa? Okay, okay, okay. Yeah, sure. So I'm just opening the table. You just check whether it is correct or not up until third iteration. Approximately, I'm saying, okay, not very specific. So this is correct, right? Now you see, we have kept the example same, both in the example one, which is to solve this system via the Jacobi method, and observe that at seventh stage, what we were getting, 186,331,423, okay, kind of thing. The original solution somewhere error with up to but three significant digit, it is same, okay. Now, if you keep on doing this with the Seidel method, you don't need seven iterations. You just need four iterations, okay, to reach to a point where the Jacobi method at fourth stage in this Seidel method, this is same as the sixth stage of the Jacobi method, as shown in the previous example. Am I correct? So what you were saying was actually correct. That Gauss-Seidel method is actually faster in the sense of convergence. So it is faster than the Gauss-Seidel method is faster than the Jacobi method. Note that only five iterations of the Gauss-Seidel method is sufficient to achieve the same accuracy as was obtained in seven iterations of the Jacobi method. This is clear to you? If not, please ask. Okay. Then let us see one example of divergence. So this is a simple example. Can you apply Gauss-Seidel and Jacobi method here? Can you do and check what happens? Yeah, but then tell me, okay, with the numbers. Yeah. Sorry, sir. Yeah, okay. Both method you see, okay, and also the original solution. Original solution is easy to see. It is 1 1. Am I correct? So you apply Jacobi method as well as Gauss-Seidel method. The original solution you can see is 1 comma 1. Am I correct? Hello? Yeah. Okay. Okay. Do. Yes, yes. This must not converge, and not only the convergence, the solution you will be getting will be very absurd. Am I correct? So are you getting this solution kind of a thing? Yeah. So you see, you are moving far and far away from 1 comma 1. And why does this happen? Because it is not diagonally dominant. Okay. So in this case, the Jacobi method diverges. Hence, you have to make sure that your hypothesis work. Okay. So here is a short note that I would like to discuss, that in the above example, the problem of divergence is not resolved by using the Gauss-Seidel method rather than the Jacobi method. In fact, for this particular system, the Gauss-Seidel method diverges more rapidly as shown in the table below. What I want to say, in this example, we saw that the Jacobi method diverges. Am I correct? So even you cannot overcome this by Seidel method. By the Gauss Seidel method, you will see that your sequence diverges even faster. Okay, so it will become worse when it is, like positively Gauss Seidel converges faster than the Jacobi method. But for the divergence also, it diverges faster, as what these examples are saying. So in this picture, the notion of diagonally dominant or strictly diagonally dominant matrix comes. So you know what is a strictly diagonally dominant matrix? Yes, precisely what is written on the screen. Am I correct? Yeah. So is this matrix diagonally dominant? This is diagonally dominant, right? Yeah. Okay, good. Now how about this one? This is not diagonally dominant because of the second row. Yeah, good. But can you make it diagonally dominant by interchanging some row? If I interchange second and third row, then it is fine, right? You will get this system. Am I correct? Yeah. Now, can you do this with this example? The problem was it was not diagonally dominant. Am I correct? Now you make it diagonally dominant by interchanging and try to find the solution by both Seidel and Jacobi method. Okay? Yeah. Yes. Yes. So you done that? Okay. So tell me. So you did this kind of interchange? Hello. Yeah, yeah. This was the case, right? Yeah. So when you do Gauss Seidel, this method, I think the first case was divergence because of the diagonal dominant case. But when you interchange, you make it diagonal dominant, and when you do the Jacobi method, so it comes like this. Am I correct? And did you do it for Seidel also? Okay. So can you see your sequence converges to one? Yeah. So we are seeing convergence. Okay. And you can also see that in this case also the Gauss Seidel method's approximation converges faster than the approximations obtained by the Jacobi method. Yeah. So let us see. Yeah. So this was all for today. If you have some doubt, please tell me. Sure, sure. Okay. Okay. I'll continue here. Just a minute. Uh, yeah. Tell me. Hmm. See, eigenvalues are actually. Do you know the significance of metrics in real life? So, and you maybe you want to put it like whenever you're solving a linear system, you actually are using the metrics. Am I correct? And can you give so? Do you agree that metrics or the linear equations appear very naturally in the real world? For example, uh, I'm just saying, let's say, uh, all these 2 cross 2 linear system you must have studied in your class 12. They were based on, like for example, this speed, the speed of this train is this, 5 greater than blah blah blah, all these kind of questions. Yeah. So, and even when you are, for example, the price of oranges is 6 rupees more than the price of apples, and one more linear equation you will give, then you will get two linear equation in two variable, and you'll be able to find the price of apple and oranges, right? So these are just very small incidents where the linear equation comes into the picture, first of all. Okay. Now think of linear equations as variable. There are n many variables in the linear equation, right? So these variables could be anything. For example, you are a student. Okay. Now you have some, let's say, you want to maintain your daily log, you want to maintain your daily expenses. Okay, then also based on that you can construct some linear equation, if more or less I'm saying, not ideally, but then linear equations is a way of expressing so many linear phenomenon in nature that happens, and that is where the metrics comes into the picture. Now let us come back to the problem of eigenvalues. Now, what is the definition of eigenvalue? Just tell me the definition first. You fix a matrix A first of all, right? You fix some A. We are dealing with, let's say, square matrix only at this time. Mn cross n r. Okay. Then we say, yeah. Hello. Mm-hmm. No, Mn cross n means the space of n cross n matrices. This is the space of the set of, maybe I'll call it set for you. The set of n cross n matrices whose entries are real. Okay. No. For example, if I say this matrix, so 2 1 3, maybe I will write just n, just to denote it's a square matrix, so one needs only this. 1 4 5 6 7 8. So this is in M3R. Okay. Yeah. What you are saying is, it's when you convert it into a map, then it is a map from R3 to R3. You can always construct a linear transformation out of a matrix Tx equal to Ax. Matrix can be thought of as a linear transformation also, but that is a different thing. Now we say lambda is an eigenvalue when do we say lambda is an eigenvalue of A? No, think carefully. I am waiting for 2 minutes, but you think carefully. Okay. What is X you did not mention? Just take your minute and tell me. Yeah, then. No, but what was the problem in the first definition? No, you have to say properly. See, this is what I would like to teach, or this is what I would like you to learn. We say lambda is an eigenvalue of A if there exists a non-zero vector x, a non-zero vector x in Rn. Okay, this should be non-zero vector. Sorry, non-zero. Just a minute. Such that Ax is lambda x. Now this definition is complete. That x has to be non-zero. Why? Because if then every number, because A times 0 will be any lambda times 0. Am I correct? So then every number will be an eigenvalue of A. That will be an absurd case. Okay. So x should not be 0. Yeah. Now physically what it is doing, before going into the importance and all, what I would like you to realize, it's geometric interpretation. Okay. To do so, I give you one example and you tell me what happens. Okay. You know how to draw vectors, right? So you take A to be this 1 0 0 1, and take A to be, or maybe B to be 1, 2, 0, 0. You find its eigenvalues and then tell eigenvalues and eigenvector. You find its eigenvalues and eigenvector. These are easy cases. You just tell me quickly. Yeah, and what about the eigenvector? Yeah, what happened? No, you find out the eigenvectors. Do you know how to find the eigenvectors? You solve this equation, no? What is the eigenvector? Okay, let me just tell you. You find it now. Okay, just a minute. So first you find the eigenvalues. How do you find the eigenvalues? We all know it is determinant of a minus lambda I. This is a polynomial in lambda. Am I correct? So you solve it. Okay. So here you know for a it is 1 and 1. Then to find eigenvector, what you do? You solve this system. Which you solve the system ax equal to lambda 1x, which is lambda 1 is 1, which is ax equal to x. So it is a linear system, right? X is unknown. So but you know how to solve this system. X is unknown. So basically when you convert it, it will be 1 1 0 0, or maybe you know that this is not a better idea to sell this out. You solve this system a minus lambda 1 I. This augmented form you solve. Okay. Can you tell me what it will be in this case? So it will be 0 0 0 0. Am I correct? Because lambda 1 is 1 and a is actually identity. So what does this system says? That every vector will satisfy this, right? So any x will satisfy this. It means you know x1 comma x2 is an eigenvector of a, is an eigenvector of a, except for all x non-zero. Am I correct? Yeah. Now you solve it for b. Okay. You solve it for b. Then I'll tell you the geometric interpretation. B also, no, it will not be same. Eigenvalue will be 1 and 2, but what will be the eigenvectors? Eigenvector corresponding to 1 you find, and eigenvector corresponding to 2. Uh, See, I think the idea of eigenvectors is not clear to you. So let's do one thing. When we meet for the next time, you revise eigenvalues and eigenvector. Okay. See, to get to know something's physical applications or geometrical interpretations, you at least should know the theory, right? Because then it will be easier for you to understand. Do you get my point? So you pick any standard linear algebra book, and there you will find many, like pick any linear algebra book and you will find. Okay. And if you still have difficulty, maybe we can discuss it the next time. Yeah. Besides that, do you have any doubt? Okay, then you may then leave the meet. So here today what we saw is the Gauss Jacobian Gauss Seidel method. So yeah. Matrix, right? Because mod A11 is 3, which is less than, because it has only one entry other than this, so it is 1. And what is mod A22? It is 5, and it is strictly less than mod A21, which is strictly greater than mod A21, which is 2. So therefore is diagonally dominant. So if you apply Jacobi method or Gauss-Seidel method on this system of equation, and you start with any approximation, let's say 0 0, then this method will, this will make sure, this diagonal dominance of this matrix, coefficient matrix A, will make sure that your method converges to the exact solution. And what are the exact solution? I think this is minus 3 and 1 for this. You see, you just check. Okay. What about this system? What about this system? 4x1 plus 2x2 minus x3 equal to minus 1. X1 plus 2x3 equal to minus 4. 3x1 minus 5x2 plus x3 equal to 3. You know what will be the coefficient matrix? See, the coefficient matrix A, it will be 4, 1, 3, 2, 0, minus 5, minus 1, 2, 1, right? Now you see, are these diagonally dominant? I think these are. You just check. Is it? See, this is not a diagonally dominant matrix, right? It's not diagonally dominant. It's not strictly diagonally dominant, right? It is not. Why? You see, yeah. So there was some misconnection. I don't know what happened. Some kind of glitch. Yeah. So in today's lecture, what we saw is the following. These iterative methods we saw for solving linear system. The one of them was Jacobi method. Another was Gauss-Seidel method. This we started with two hypotheses of Jacobi method, which is the first is, like the solution should always exist, then the conditions on the diagonal entries. We saw step by step algorithm. Yeah.
So maybe we could finish here. We saw some examples. Yeah, just focus on an example for a while. So yeah, these two methods, as we have discussed by these examples, play a crucial role in the numerical analysis technique and helps us to find iteratively the solutions of a given linear system where it is difficult to find the direct possible solution to the given linear system. But as any other method, it has certain drawbacks, as explained in example 3, and how it can be overcome. It has also been explained in example 4. So, yeah, see you next time.